Hi everyone, so today I'm going to be talking about impossible integrals and Feynman's technique of integration. So I want you guys to start by trying to figure out these integrals with the current calculus knowledge that we know. I'll give you a couple of seconds. The truth is, they're not doable with what we already know. So how can we make them doable? Well, that's where Feynman's technique comes in. So, what even is the basic concept of Feynman's technique? So, Feynman's technique is often applied to integrals with a single variable. The idea is to artificially introduce a second variable and then build a differential equation in terms of derivatives with respect to the new variable. Solving this differential equation often allows us to compute the original integral. So, in order to actually understand Feynman's technique into a deeper understanding, first we need to know what a partial derivative and what a parameter are. So, what is a partial derivative? Well, in calculus, a partial derivative is a derivative taken of a function with respect to one of its variables while keeping the other variables constant. It generalizes the concept of a derivative to functions of multiple variables. So, I want you to consider a function f of x, y, and z that depends on multiple variables. The partial derivative of f with respect to x represents how f changes as x changes, while y and z remain constant. So why is the partial derivative important for Feynman's technique? Well, as a whole, Feynman's method allows us to simplify a nasty-looking indefinite integral by differentiating under the integral sign. And you can differentiate the inside of an integral as long as it is a partial derivative, basically. So, in addition to the partial derivative, you guys will need to know what a parameter is. So, in the concept of Feynman's technique of integration, a parameter typically refers to an auxiliary variable introduced into an integral to simplify its evaluation. This technique often involves introducing a parameter through a clever change of variables, or by differentiating or integrating with respect to the parameter, allowing for easier manipulation and ultimately leading to a solution for the original integral. So these are our example problems. It seems that the problem can't be solved using the usual techniques. So you guys might try integration by parts or substitution, but you could spend hours working on it and finding absolutely no solution. So that's why Feynman's technique is really useful. So we're going to begin with this problem. This is probably one of the most used problems when teaching Feynman's technique. So the first step to this will be introducing the parameter. So first we introduce a variable other than what we're integrating. And in this case, we're going to call it t. And we're going to put the t right here, right in the exponent of x. Now, where you put the t is going to depend on the type of integral. And it's typically going to have some trial and error because we have to constantly think of where we place a t will allow for the best manipulation of the integral. So now we're going to define this as a function of t, g of t. So what basically we want in this case is we are trying to find, in the end, g of 1. And the reason for this is because originally this will be x to the power of 1, as seen. It's x to the power of 1. But since we're now putting a t above the x's exponent, that basically tells us that t is equal to 1 and g of t is g of 1 for what we are solving. Next, we're going to differentiate partially the function with respect to that parameter that we have just introduced. Now for this, it is obviously going to be really hard to take the integral of this. It's going to be very difficult to take this integral. However, it would be very easy to take the derivative with respect to our new parameter t. And the reason we are able to even do this is due to the concept of Leibniz's rule, the partial derivatives, which allow us to bring the derivative literally right inside the integral, and then we can differentiate it. And when we actually differentiate it, since the entire concept of the partial derivative is that t is now our variable and x is a constant. So when we differentiate This ln of x stays there, and x to the power of t will become ln of x times x to the power of t, and 1 will just be 0. So you may notice how absolutely amazing this is. This ln of x right here can cancel out with this ln of x in the denominator, and just leave us with the integral from 0 to 1 of d of x. So when we evaluate this integral, this integral right here, we just end up with g prime of t is equal to 1 over t plus 1. This is just basic calculus that we already know of. But the issue is, we don't want g prime of t, right? We want g of t. So we need to take the integral of g prime of t, basically using the fundamental theorem of calculus. Now, if we integrate this, we're going to be left with a really annoying constant. So what we can do instead is we can add limits. So we can make this the integral from a to 1. If we take the limits from a to 1, where a can be any number we want, we'll be left with g of 1 minus g of a, right? And now we need to find out, what is g of a going to be? Well, if you think about it, let's say we set a equal to 0. If we plug in 0 into this ln of t plus 1 when we're plugging in a, which is 0, we will get g of a is equal to 0. And that just makes our life so much easier. Since now that we've replaced g of a is equal to 0, we're just left with this equaling to g of 1. And when we simplify that by just putting the 1, subtracting it by the 0 value, we will get ln of 2, and boom, we're done. So now we're going to try another example. So for this function, I feel like the first step is that we can notice that this is an even function. Thus, we can rewrite this as the integral from 0 to infinity of sine x d of x times 2. Now to actually dive into the Feynman's technique. So the first step we're going to do is we're going to introduce a new function by introducing this parameter t. We can call the parameter anything, but by convention, I like to call it t. And we're going to introduce this factor, just kind of magically insert it inside the integrand. And what we're going to insert is e to the power of negative tx. And you might wonder how we know what the actual parameter needs to be. Well, luckily for this test, Mr. Sproul is going to actually give us the parameter. So, but as time goes on, you'll understand more about what parameter you need to use as you keep solving more and more problems. But for now, just bear with me on why I chose this parameter. Something to understand is that we want g of 0 in this case, and the reason that we want g of 0, like the last problem, we wanted to find g of 1 since we set t equal to 1. The reason that we want to find g of 0 this time is because when we make t equal to 0, it will just give us the original function that we're dealing with, the sine of x over x, the original integral that we're dealing with. And yeah, so the next step we're going to do is, now we don't know how to find the integral of this, but just like the previous problem, we do know how to find the derivative. So we are once again going to use a partial derivative with respect to t. And now that we've done so, we will understand that e to the power of negative tx, that will give us negative x e to the negative tx. And once again, isn't that so useful? Because now the x's cancel out, and we're left with g prime of t equaling this. And using integration by parts, we can simply simplify that into negative 1 over 1 plus t squared. But the issue is, now again we have g prime of t, but we want g of t. So we're going to take the integral of this by the fundamental rule of calculus. And yeah, so just look at this now. Tell me, does this look familiar to you? And the truth is, yes, it does. The reason is it's a trig sub. So we can further simplify this into understanding that g of t is just equal to the negative arctangent of t plus c. But once again, we have another issue. We are left with this super pesky integration constant, this plus c. So in order to find g of 0, we need to first find this integration constant. And the way that we're going to do this is you can notice how in the previously before we simplified and did all this Feynman's technique, we knew that g of t is also equal to the integral from 0 to infinity of sine x over x e to the power of negative tx d of x. And also now we know that g of t is also equal to the negative arctangent of t plus c. So we can just simply set them to be equal to each other. And what's super amazing about this is the trick that we need to notice is as the limit of t goes to infinity, what happens on the left side is this will become 0, making all of this become 0. And in addition, as t goes to infinity, the arctangent of t, the negative arctangent of t, will become pi over 2. And with this negative sign, it will become negative pi over 2. So we will be left with 0 is equal to negative pi over 2 plus c. Algebra, c is equal to pi over 2. So then we can actually simplify our g of t statement to become g of t is equal to the arctangent of t plus pi over 2. And as we previously knew, we want to find 2g of 0. We want to find g of 0 because that is what our parameter allows us to, and we want to find 2g of 0 because it's an even function. We simplified this original function to become 2 times g of 0 right here. Whoops. One more. Okay. So let's plug in 0. The arctangent of 0 will just simply be 0. So thus, g of 0 is equal to pi over 2. And we just multiply that, and we get pi. Wasn't that super good? So yeah, now I'm just going to give you a huge recap about the generality of Feynman's technique. What's a super quick understanding of it? So first, you need to make a function that is the integral with an extra parameter. Next, you're going to set the original integral to a value in the function. You're going to differentiate partially the function with respect to that parameter. And you're going to hope that the integral is now easier to evaluate and actually evaluate it. And if it's not easier to evaluate, you will need to go back to step 1 and identify a new place to place your parameter. Then you're going to integrate with respect to the parameter, and you're going to find c as we did previously by plugging in these easy values for the parameter function. You're going to finally plug in that value to get the original integral, and you're done. Thank you guys so much for listening, and these are my citations. Each of them have been super useful, so check them out if you have any more questions. Thanks.